So I'd like to thank the organizers for the invitation. This is my title. It's based on the work with Grisha. In progress, I take the sole responsibility for the talk, which I would like to dedicate to Uriel and his visa problems. Uriel has been a source of inspiration to me for years. He was certainly to most of you. I have to warn you that this is going to be a little bit, talk about a little bit academic problem. But since we are celebrating academician, that maybe not completely out of place. You can also view it as a quick response to Uriel call for non-standard analysis. Well, in a paper from '66, Arnold noticed that incompressible Euler equation describes geodesic motion on the group of area-preserving diffeomorphisms. It implies in particular that you can write Euler equation and geodesic motion on any space with a Riemannian metric, and it sort of looks almost like in flat space, except that in the convective term the derivatives are covariant, and you use the metric, inverse metric, to build the gradient of pressure and the incompressibility condition since the metric volume of the space. That probably was known before, but you know the history well. This write up in other spaces, in other metric backgrounds. But I mean, this observation also sort of tells you that there is a variational principle behind. So if there's variation principle, then the sort of symmetries via Netter procedure give rise to conserved currents. So conserved currents here mean that. And we will be looking in two-dimensional situation, with hyperbolic plane, two-dimensional space, as you will see in a moment. So there, I mean, incompressibility means that you have a string function related like that to the velocity, and well, the vorticity is introduced like that, and it's still carried by the flow. And if you write the equation in terms of omega and psi, that picks up 1 over the square root of the metric body. It looks almost like flat space, but there are differences. Okay? Well, you can go to Navier-Stokes equation by adding a viscous dissipation in a geometric way using the Laplace-Beltrami operator, sort of Laplacian in geometric setup. And you can add the force. In 2 dimensions, we'll sort of assume that force is a Gaussian process decorrelated in time, and the covariance, because of this string function picture, can be just given by a function, a scalar function, which I take as a function of geodesic distance divided by some scale. So this will be this forcing scale if you assume that the function c sort of decays fast. Arnold looked at hydrodynamic equations in general geometries to study the topological aspects of flows. There's a book about that. Our sort of motivation was to look for, came from the desperate look for the understanding of the conformal symmetry. It sort of was seen in the inverse cascade in 2 dimensions via this discovery of the SLE statistics of zero vorticity lines. It's a very mysterious thing. Well, the main idea was that maybe in some other 2-dimensional geometries supporting the inverse cascade, you can sort of see a source of conformal symmetry easier. And to cut the long story short, let me just tell that in some sense, as you will see, this is the case for the flows on this hyperbolic plane. But unfortunately, we haven't yet made any connection with SLE statistics. Maybe it will come, maybe not. Well, so why hyperbolic plane? Well, what is it? It's a two-dimensional space with three-dimensional symmetry group and a geometry which has a constant negative curvature. And sort of Ricci curvature has this factor 2 Gaussian curvature result. Why not using the sphere, which is sort of simpler space, which is two-dimensional, has positive curvature and a three-dimensional symmetry group? Well, just because there is no space there to develop inverse cascades. Well, just no long distances. So the cascade will be blocked soon. It will develop the large-scale structures. However, hyperbolic plane has infinite volume and a lot of room and large distances. So, for example, the circumference of a circle of radius rho here grows exponentially at large rho. And so there's more space at large distances than in flat space. So, in principle, there is no geometric mechanism which would stop development of the cascade. Problem is that, in some sense, it overflows. So, what is this hyperbolic plane? Well, there are various ways to look at it. You can view it as an upper half plane with a metric which is flat divided by imaginary part squared. You can view that as the sort of created hyperbolic geometry in 19th century, Lobachevsky and Bolyai, I mean, in a sort of more complicated way. You can view it as a Poincaredis, but most convenient for us would be to view it as an upper hyperboloid in the, well, one sheet of the two-sheeted hyperboloid in the three-dimensional space with a Minkowski metric. Okay? So the metric on this beast will be just inherited from the Minkowski metric, but if you, which is not positive definite, but if you restrict it to hyperbolic, it's positive definite. Okay? So that's the way we will view it. So this will be just Navier-Stokes on that object. Okay? So from this picture, you see that the isometry group of this upper half plane is the three-dimensional Lorentz group, which is also the SL2R group of matrices, 2 by 2 real matrices with determinant 1 divided by its center. Okay. And convenient parameterization, which we'll use of this hyperboloid, is just radial or axial, rather variable, r and phi. So in terms of them, the stream function is related to velocity components Vr and V phi like that. Vorticity is given by Laplace-Beltrami operator applied to psi, and the Euler equation just in terms of stream function is here.
Christoph, sorry, may I ask a stupid question? What about invariants? They are still there, or vorticity and the energy are still there with the right metric?
Yeah. Okay. Well, I mean, I won't care much about this the entropy, which is there, okay? Because I want to sort of push it to the end where I don't look. Okay? So I will talk about the inverse cascade. Okay? Well, but there are sort of these net symmetries. Well, one of them corresponds to time translation that gives you current whose zeroth component is the energy density. Well, then the ones corresponding to these Lorentz rotations, they give you just 3 components of what you would like to call momentum in this case. However, well, what you screwed up is the Galilean design. There's no part of it, which sort of may cause problems.
On the curved space, it's always accelerated motion. No Galilean.
Well, in Navier-Stokes, I mean, you have again if you add also the Gaussian forcing as we were describing, you have energy balance. I mean, sort of the rate of change of mean energy density would be given by dissipation rate and injection rate, which is related to the second derivative of this forcing covariance. Well, so in flat space we have this inverse cascade scenario, in fact both cascades, but we will look at inverse cascade by placing the forcing scale in the middle with a scale where it dissipates entropy by viscosity, viscous term much smaller, and we'll look at scales much larger than the forcing scale. So there are scales where you will see the energy flowing to the essentially to modes close to constant mode. I mean, sort of asymptotically, you'll be building the energy in the constant mode. And if you look at the two-point correlation of stream functions, you will asymptotically at large time see the term, quadratic term distance growing in time, plus a stationary term proportional to distance to power 8/3, plus terms which do not contribute to the velocity two-point function. Disappear when you take the derivative. So, well, we postulate that you have still such a scenario on this hyperbolic plane, where you will have this condensate mode growing linear in time and stationary mode, where plus things will disappear when you go to velocities. And just by symmetry reasons, these things will be functions of the hyperbolic distance between the points, or for convenience we express them as functions of hyperbolic cosine of the distance divided by this curvature radius r. Okay. So here we have one more length scale present, which will take this curvature radius, which will take much longer than the forcing scale. I mean, in this scenario, of course, for distance is much smaller than the radius, curvature radius. Space is essentially flat, so you'll see the standard, the previous picture. So these things should be like in the flat space in this region. Among other things, it means that energy injection is given by first derivative of psi 0 at 1. But which you try to find how these guys are modified on large distances, on distances much larger than the curvature radius where you see the curvature. So, and we'll try to determine by scaling articles. So, well, at the end, I think the scenario up to now seems to us self-consistent. But of course, it is a sort of an assumption. I mean, sort of should be tested numerically, I think. We don't have proofs. Well, so scaling theory. So let's take the velocity correlator at equal times, n point with m r components and n minus m phi components. So, well, if you sort of stare at it and look at the equations, you will see that this correlator on the hyperboloid of curvature radius r with viscosity nu, forcing covariance c, and the forcing scale L is related by scaling to the similar object on hyperboloid with r divided by lambda. Well, then viscosity rescaled and forcing scale rescaled, and that's just a tautological relation. If you look, I mean, things are arranged so that the powers are arranged so that the energy injections, injection rates on both sides are the same. Okay? But you have different spaces here, okay? At least spaces with different metric on both sides. Okay? Well, but if you stare at it, you can think that it seems plausible that the right-hand side has a limit when lambda goes to infinity. What this limit would be, I mean, this would be some sort of a theory on H0, okay? And H0 is just a light cone in this Minkowski space, okay? Where you sort of inject the same thing all the time, okay? Viscosity goes to 0, so it's some sort of force Euler on this, on our limit of vanishing viscosity of force Euler on this light cone. Okay? So if the scaling limit exists, it just gives you the asymptotic behavior of the correlations on the fixed hyperboloid at large distances and large times. So that's sort of the basic assumption here about existence of the scaling limit, which has some caveats, as we'll see. But essentially, we are trying to exploit the geometric effect that far away the hyperbola just looks like a light cone. To see whether it's plausible to have this limit, let's look at the Euler equation on this light cone. Okay? It still makes sense. Okay? In fact, H0, which we use parameter the same way as HR before, it inherits metric from the three-dimensional Minkowski space, but this metric is now degenerate because it vanishes in the light cone directions. Okay? That's what light cone is, 0 directions of metric. Okay? But as a result, it has a big isometry group. The isometry group is the reparametrization of phi. So it's the diffeomorphism group of the circle. So that's a one-dimensional conformal group of half of two-dimensional conformal group. Two-dimensional conformal group is dFs1 cross dFs1, two copies. Okay? And it's an infinite-dimensional group, which in particular contains this three-dimensional Lorentz group. A remark which may be sort of inspiring for some people, but not for you probably, is that this is exactly the same way as conformal symmetry arises in this ADS CFT correspondence you might have heard about, which sort of keeps busy many string theories, high energy people, and so on. Because this is sort of a lower dimensional version of hyperboloid of ADS space. In terms of stream function, which gets now related in a simpler way to velocity, and sort of what's left from vorticity, I mean, it's just these two derivatives of stream function in r direction. Euler equation looks sort of as if it were a flat space, but the relation between psi and omega at the end. So it's a simpler thing, I mean. Well, what about Netter symmetries? Well, there are still the ones corresponding to time translation, because there's time translation invariance, so that's the energy density. But there is an infinite number of conserved quantities related to this dFs1 symmetry, and they give rise to those currents. So integrals of these things are multiplied by any function of angles is conserved, which means that integral of r squared v phi along any light cone is conserved separately. Well, however, if you look at the scaling limit by which we are getting at this H0 theory, okay, which had some force in it, so it appears that the symmetry will be spontaneously broken. In fact, I think it's a sort of, one should really well understand in which way it's broken, because broken symmetry is that thing which sort of theoretical physics is made out of. I mean, it's made out of the stories how to use the broken symmetries. The scaling limit, when it exists, tautologically just obeys the scaling relation, where on both sides now you have the same light cone, H0. We can look for solutions of this relation. Okay? And for two-point function, there are just two solutions I want to sort of write. One is linear in time, okay, plus there is a logarithmic correction. Okay? And another one is stationary, which is proportional to third power. These are the solutions of these scaling relations, where x is here sort of an SL2R invariant on this light cone. There's no distance on light cone. Really, distance between 2 points is 0 always. I mean, this is the invariant. Some sort of limit of rescale distance. So what this means, I mean, in this inverse cascade condensate scenario, is that these solutions sort of give you the large X behavior of the condensate mode and the stationary mode. And these are how these behaviors look. Well, there is a little bit sort of story about the sort of this logarithmic term it appears, in fact, that the VR two-point function doesn't have a scaling limit and misses it by a logarithm of lambda. Okay? So if you try to absorb this logarithm of lambda, you absorb this term here. It doesn't appear.
So these averages now are over the statistics of the forcing?
Yeah, they are over statistics of the forcing. You had also time, so you start from 0, for example, to force to average. And the forcing was so that it was covariant under the symmetry group. Okay? So, well, I mean, what should you look like? I mean, well, in 2 dimensions, you often make just the invariant two-point function by taking scalar product of 2 velocity vectors. You can do it here too, and the way you take scalar product is just attach those 2 velocities as vectors to tangent to the hyperbola, and you take their Minkowskian scalar product. That's the invariant two-point function. Okay, so that it's just expressed by this two-point function of the stream functions, just by 2 derivatives over the argument like that. So out from this large x behavior of these guys, you get the behavior of this two-point function. So for example, it means that the term proportional to time here, which behaves, which is a constant proportional to injection rate for distances where you don't see the curvature, so in flat space. I mean, for distances much larger than the curvature radius, it decreases linear in hyperbolic distance instead of being constant. The stationary contribution, which is for small distances like that, for large distances, this is the usual structure function if you want. For large distances, it sort of gets negative, increases in absolute value exponentially in the distance. Well, I mean, we're sort of trying to see if there's no contradiction or realizability things, you know, or in plain language, Schwarz inequality for two-point function. But I think there is none. So it's consistent, but physics is not very clear, except for sort of that these sort of large negative things are essentially a geometric effect. Well, there is a spectral interpretation of all these objects, but this would carry us too long into mathematics because you have to know how to do Fourier analysis on this space. So of course, it has been done in mathematics a long time ago. So here is how this condensate contribution to invariant two-point function looks like. Instead of being constant, it sort of falls down. Well, we are sort of gluing this value at 0 with the known behavior for large R. So, well, if you do it literally, then I mean it goes down quite quickly before you reach the curvature distance. But well, I mean this is not completely reliable. This region intermediate region. Well, we have also flux relations. Just like in flat space, you have this sort of relation which tells you that the two-point function built of 3 velocities in this way is proportional to ejection rate times the distance. I mean, here you have sort of similar relation, except that you have this expression on the right-hand side with this condensate mode here. And if you look at it, it sort of looks funny because, well, for small distances, it's not like in the flat space proportional to 1/2 injection rate rho. But at large distances, it just changes sign. So you may be tempted to say that some sort of flux changes sign, but that's not the correct interpretation. We don't really sort of have a sufficiently good interpretation. Well, that's more or less how much we have, except for the sort of spectral things I don't want to talk about, so let me sort of conclude. So it seems that this type of inverse cascade condensation scenarios for the NS on hyperbolic plane seems consistent. You can get the behavior, asymptotic behavior of these contributions to the two-point functions just by scaling limit, which leaves on the cone. The theory on the cone sort of has a diff S1 symmetry related to conformal group, as I was trying to tell you, but not in a very simple way. So this would be an asymptotic symmetry, which besides is sort of spontaneously broken. I mean, conformal theory, most of the time well, I think always you break the spontaneously conformal invariance, although it's not usually presented this way. So I think it's very important to understand how it's broken, because it might be sort of a clue to linking to the properties of the vorticity lines, this business. Well, I think that what we really need here to push further the story would be numerical simulations. Unfortunately, it's not very easy to. Well, I'm not a numerical person, and it's difficult to persuade somebody to do it because it's a little bit academic problem. You might have noticed, and the reason essentially is that you have no sort of, you cannot embed this hyperbolic into three-dimensional Euclidean space. In fact, it's not known whether you can embed it into four-dimensional space. Not even strictly speaking known whether you can do it in five-dimensional space. There is known embeddings in six-dimensional space. So somehow you cannot realize this with soap films and things like that, which is sort of said message. Well, however, soap films can sort of give you maybe some idea how the curvature influences inverse cascades, so maybe situations not totally hopeless to connect with some experimental things. I tried to... Well, that's essentially the end. I mean, I tried to find a picture of Uriel in the outfit of academician. I didn't find one. Unfortunately, it doesn't seem to exist in the public domain. Never happened. Must have happened. No, even when you were at the inauguration.
Of course, yeah.
No. Well, what I found is the picture you have seen already of Uriel with all hair raised by the stock. So let me finish with this appeal to you. Thank you.
Krista, we have a numerical code where kind of if you give the Gij, we can solve the Navier-Stokes equation. We need to make some modifications because we actually solve it on the surface of a sphere and by finite difference, not by spectral. As you said, spectral would be difficult because you have to understand how Fourier transform will work here.
Well, it's, everything in that domain which has to do with numerics is difficult to me. It's probably easy for you. I mean, these things are probably in the C library and...
But I guess you will have a singularity, numerical singularity at the axis?
No.
No?
No. No, because the axis is where you are flat.
Okay, that's...
Coordinate singularity.
Yes.
Yeah, well, if you use these coordinates. I mean,
Yes.
In fact, there might be not... They're sort of nice to do this scaling limit, but they're not the most convenient coordinates on the upper half plane. The convenient coordinates are the conformal coordinates.
And what kind of boundary condition do you imagine would be required?
No boundary conditions. You sort of start forcing, but this is infinite space. Sort of, you start forcing with things which sort of will build start building the motion, the velocity in the middle, and then it will sort of go as
But in computer there are no infinite space. So it will be periodic. If you do spectral, that will be periodic boundary conditions.
No, I don't think it will be periodic boundary conditions.
Maybe this one, the other one?
I think you probably sort of would have to put the friction and sort of then cut it whichever way you do it.
No. Yeah, Christoph, there's some problems are much more easily formulated in physical space and other more easily in Fourier space. Is there any way you can formulate this curve problem in Fourier space?
You can formulate it, of course, in Fourier space. The problem is that when you sort of have superposed two plane waves, well, the result is simple. When you superpose two waves, which correspond to Fourier modes here, you get an integral over all sort of Fourier modes. And well, that's sort of Clebsch-Gordon's in this setup. So I think the equation, you should sort of go at least back from spectral to real space and do multiplication there.
Yeah, of course.
But otherwise, you can sort of... The Fourier transform itself is simple. Okay? The Fourier transform of the product expressed in Fourier transform is complicated.
I have a simple question about Galilean invariance. I understand you can't have Galilean invariance on a sphere because you cannot have a constant velocity on a sphere. But there, this space is homogeneous, and so why don't you have a constant velocity?
Because what doesn't mean constant? Okay, that's a coordinate-dependent statement. Velocity is a vector. Well, you can sort of say that you look for the vector which is parallel.
Yeah.
No such vectors because of curvature.
Think about the sphere. I mean, if you move on a sphere with a constant speed, it's still an accelerated motion.
Yeah.
And then it's not equivalent to stay at rest. In a flat space, it's equivalent. But now the moment you change direction of velocity, that's it. You accelerate it.
But you have local Galilean invariance. I mean, in an infinitesimal domain, you can do a local.
Well, as long as you're sort of flat here, you
it's
also
locally
have it,
flat.
but
Then you
sort of, once you go to distances.
Anyway.
Kind of surprise.
Okay, but I'm afraid the questioner has to cede to Barsha the speaker. Yes. So thank you again.